Hey, Mr. Younger.
Logan, how you doing?
Good, how are you?
Great.
So, is the next chapter that we're doing chapter 36?
Normally, yes. So what we are doing is we're finishing well, yeah, it's almost always 36, but what we're doing is we're going to go through 10 and then 11, which we'll finish up 10 tonight. And then we normally jump to 36, but that's sort of an extra thing. So I've decided to go to 14 and 15 next. And then if I finish that in time, I'll go to 36. But otherwise, I have to cut 36 out because that's relativity. And nobody's expecting you to have relativity or quantum mechanics or nuclear physics if you've only had two semesters of this course as opposed to 3 semesters.
And I also had another question actually about next semester. So, I wanted to take 242,
Mm-hmm.
but me and my advisor were looking, and the only virtual option is with you at 5:20 to 6:40 on Tuesdays and Thursdays.
Right.
But I'm required to take chemistry, and my lab is from 6 to 8:15 on Tuesdays and Thursdays. So I wanted to make sure it was okay if like I would leave early every Zoom meeting and I could just watch like the recording
Yeah,
because
I
there's
can work that out
no.
for you. And I think our lab is supposed to be after that lecture. So if you want to, you could attend my day lecture. Uh, and if we have to do it on the books, we can. But there's going to be a limit to how many people I can accept because we can only fit so many students into the classroom. But if you wanted to do the day lab, I could make that happen for you if necessary.
Okay, thank you.
No problem. Yeah, I work with you guys. I try to do as best I can to help y'all out, even if you're taking it online, and even if you can't attend regularly, as long as you can access the videos and you think that's good enough to help you, then you can do that. But usually it gets kind of hard, so make sure you shore up some time that you can contact me by Zoom or set up office hours or Zoom office hours or something so that I can help you when you're missing stuff.
Yeah, I will for sure. Thank you.
You're welcome. Anybody else have any questions? We got about 2 minutes for class starts, so feel free to ask me any questions.
Professor Younger, I have a question.
Yes, John, go for
Is it too late to take the Proctor 2 exam?
it. You mean chapter 2, or you mean
No,
like
the
just
one that was given last Monday. I know
the second midterm?
yeah, I know I asked for extension, but my work week was a lot longer than I thought it was going to be.
Yeah, you sent me a message about that, didn't you?
Yeah, I did. I
Yeah,
tried to do it last night, but then I couldn't access it.
yeah, it's not a
Also,
problem. I'll go ahead and set it up and make it available for you. Do you want to do it tonight or tomorrow or what?
tomorrow will be better because I do have a lab after this.
No problem. Yeah, I'll set it up for tomorrow. Let
Okay.
me right now while people are here. I got about a minute, so I should be able to fit it in. If not, remind me to after at the end of class just to make sure. I think I can fit it in real quick. Second
All right, we'll
minute.
do.
All right, thanks.
Thank you.
All right, I did get that set, John. It's available tomorrow. Everything should be ready to roll. Text me if you run into any problems when you're trying to take it. So that way I usually get, I get text messages in real time, and I usually can reply to them or at least look at them and see if I need to reply to them immediately. So if you have any problems when you go to take it tomorrow, just text me. Anybody else have any questions? It's about time to start class. All right, it looks like we've got now 10 people in here. So actually, no, we're up to 11 now, I think. So we've got basically just about everybody, and it's time to start class. Last time we had started on doing some of the dynamics of rotational motion, which I was telling my students today. There's a concept called mechanics, and that's what we're studying in the 241 sequence is basically mechanics, which includes kinematics and dynamics. The kinematics, as I told you, is just the study of motion, predicting where you'll be, how fast you'll be going, how what direction, that sort of stuff. That's all kinematic stuff, where you can explain the motion just by knowing, in detail, like its position as a function of time or its acceleration as a function of time with appropriate initial conditions. And then anytime later in time, you can predict exactly what's going on, but you don't have any idea of what actually caused the acceleration or even how to figure out what could cause the acceleration because you just don't have the dynamics portion. And the dynamics portion is that portion that covers some of the kinematics in principle, but generally it's separated into the stuff as that says what causes the acceleration, which you guys recognize as Newton's second law. So that's what we're doing now is sort of the equivalent of Newton's second law, but it's the Newton's second law for rotation, which we learned was the summation of the torques is equal to I times alpha, or I times d2 theta over dt squared, or I times d omega over dt, or even dl dt. So let's get started with that. Last time I worked a problem with a Atwood machine, and I think we had made a little careless mistake. Actually, let me look at it and see if I remember. I'm trying to look. Yeah, it looks like we had made a little careless mistake in the sign. I'd found, or actually Mika had found it. And in fact, what you end up getting there, I can give you that real quick. I'm going to go ahead and share my screen with you guys. So let's share screen. And today, basically, I worked it out in lecture for my students and then literally did the tensions and all that good stuff. So I wanted to give you what the ultimate result was. And y'all can figure that out. I basically set up everything right, but I got one of the signs wrong. That made it a problem. And of course, that's a pretty significant problem. So what I'm going to do is I'm going to go back to page 13 of my notes, actually page 11 of my notes. And what I'm going to tell you is that the acceleration for that turned out to be m2 minus m1 over m1 plus m2 plus 1/2, plus 1/2 big M, all that times g. That was the acceleration. The alpha is equal to m2 minus m1 over m1 plus m2 plus 1/2 m times g over r, where r is the radius of the pulley. I found that T right, which is the side that the mass m2 was hanging on, was m2, 2m2, actually, no, excuse me. It was 2m1 plus 1/2 m over m1 plus m2 plus 1/2 m times m2g, and T left was 2m2 plus 1/2 m over m1 plus m2 plus 1/2 m times m1g. And notice that since m2 is supposed to be greater than m1, then T right will be greater than m2 than T left, specifically because T right not only has to lift the mass M1 up at the same acceleration that M2 has downward, but it also has to rotate the actual massive pulley, the pulley that has mass. So that's why that came out. But that's the ultimate result from all that. If you need to see it or anything, by all means ask me. But basically, that just took a lot of algebra is all it was. So the original equations that we had in here, for instance, you can see in fact, what's going to have to happen is this quantity right here is going to turn to a negative, and you'll see that that actually looks just like the acceleration I had here. And then, of course, you can get alpha because A equals R times alpha. So alpha equals A over R. So you can see why that's G over R. And this actually looks a lot like the Atwood machine with no mass on the pulley. And just as a reminder, that was the acceleration for the Atwood machine was M2 minus M1 over M1 plus M2 times G. And the tension was 2M1 over M1 plus M2 times M2G. So that's normally what the Atwood machine was, but now you've seen how it changed that a little bit and gave us a little bit more of an understanding. Okay. Yeah, and of course you should. This is part of the reason why you do stuff like this is you could imagine that this problem was worked with a massless pulley, in which case you just replace the big M with 0. And what you'd see is then you'd end up getting exactly the same results as I have in blue here. So that's one of the keys to physics is every way you can solve a problem you would like to try to, and then compare all the ways that you possibly can and see that you get the same result every time. If you don't, there's some new learning to be happening there, or there's some errors that were made. So anyways, I just wanted to give you that. It'll be in the notes now. You can see it's on page 11, which is the last page of these notes. So you can see it there, but you can also work it yourself to get the full results. And if you have any problems, just let me know. Okay. All right, we're going to continue on with the same chapter doing dynamics. In this case, I have a certain pulley has a mass of 4.25 kilograms and a radius of 40 centimeters. It has a soft rope wrapped around it and a constant force of 20.0 newtons applied to the rope, while friction causes a torque of 3.00 Newton meters to fight the rotation. Assuming that the rope does not stretch, get slack, or slide on the pulley, what is the moment of inertia of the pulley if the pulley starts at rest but reaches an angular speed of 45.0 radians per second in 4.50 seconds? So that's our problem. Let me draw it a little bit so we can make some sense of it. Anybody have any questions on how I worded that or anything that you don't understand about this problem? So we're going to draw a pulley like so. And basically what I'm going to have is a constant force. F is equal to 20.0 newtons pulling down that way. The radius here is R, and the mass here is M. And that is, in fact, the free body diagram. I would only say that the inclusion that I need to make it a free body diagram is that T friction is going to be equal to 3.00 newtons per meter. And I'm going to go with the sign convention that this is the positive direction. And because of that, that means down on the left would also be the positive dimension or direction, and up on the right would be the positive direction. Again, just doing this kind of thing keeps you from having to put spurious negative signs in equations like A equals R times alpha and stuff like that. We're not even going to need these bottom two on this particular problem, but I wanted to show it to you anyways. So let's go ahead and write out what Newton's second law, quote unquote, for this type of motion tells us. So the summation of the torques is equal to I times alpha. as I said, any torque that causes a rotation in the counterclockwise direction, I'm going to consider that to be positive. So I think you can see that torque, and this is kind of important, by the way. Let me draw this just to make sure everybody knows what I'm talking about here. So if you notice the line that connects the center of the pulley to where the string makes connections, it looks like that's a 90-degree angle, and that's the general rule. Basically, when a rope pulls off of a pulley, it generally pulls off when the rope is tangent to the surface, so that the torque need not have the sine theta term for it. Basically, the torque is going to be the radius times the actual force. So in this instance, we know R, I should have written this down here, R is going to be equal to 40 or 0.400 meters, and M is going to be 4.25 kilograms for the mass of the pulley. So we can go ahead and write this out. We're going to say 0.400 meters, that's the radius, times 20.0 newtons minus 3.00 Newton meters is equal to I times alpha. So what we're asked for here is the actual moment of inertia. So what we're wanting is I equals question mark. So I've got this equation right here, and that allows me to get the left-hand side. However, I need something for alpha, and basically we're given enough information to get alpha, and that information is that alpha is equal to delta omega over delta t. And I wanted to, I don't think I actually wrote it this way necessarily, but basically you can assume that this acceleration, this angular acceleration, is a constant, because clearly the force is constant, and the tension, or excuse me, the friction torque is constant, and the moment of inertia shouldn't change. So this is really going to be a constant acceleration, and therefore you get 45.0 radians per second is the final angular velocity, minus 0 radians per second. And then all of that is divided by a time period of 4.50 seconds, which I think you can tell is alpha equals 10.0 radians per second every second. So anybody have any questions? So that's going to be equation 2, and this will be equation 1. When I multiply 20 times 0.4, that's going to become 8, and then 8 minus 3 would be 5. So equation 1 will give us 8.00 Newton meters minus 3.00 Newton meters is equal to 5.00 Newton meters, and that all is equal to the summation of the torques. Okay. Now, we also know that the summation of the torques is equal to I times alpha, so that means I is equal to the summation of the torques divided by alpha, and we just calculated the alpha. So we can say I is equal to 5.00 Newton meters. Your book's writing this as meter newtons, and that's fine too if you want to. I'm used to calling it foot pounds and stuff like that, so that might be why he's actually writing as meter newtons. But either way, it doesn't matter too terribly much. What you see here in this case is the alpha is 10.0 radians per second. And of course, a Newton is a kilogram meter per second squared. So when you multiply it by a meter, you get a kilogram meter squared per second squared. And then you're dividing by second squared. The radian can just be dropped because that's not really a unit. So what we're doing here is we're dividing 5 by 10, and you get 0.500, and all the units you have left are the kilograms. Oops, let me rewrite that. That did not turn out too pretty. Are the kilograms times the meters squared. And that's the moment of inertia for this particular pulley. Any questions on that? Now, typically, I think if you just look at a pulley, you might say it sort of looks like a cylinder. And just for context of what this moment of inertia is, I should write down that the moment of inertia for a cylinder is equal to 1/2 the mass times the radius squared, which for this case, if this were a cylinder, we'd get I cylinder equals 1/2 times the mass, and the mass was 4.25 kilograms, and then the radius is 0.400 meters squared. So you get 0.4 times 0.4. That's basically 4 over 100. 4 times 4 over 100. That's 0.16. If you multiply that by 1/2, you get 0.08. And then if you multiply that by 4, well, heck, that's just getting to be a mess. I'm going to go ahead and calculate it. So 0.5 times 4.25 times 0.4 times 0.4. And that gives me 0.340 kilogram meters squared. So clearly this thing has a bigger moment of inertia than a cylinder of equal weight and equal radius. But that, I think, hopefully is to be expected. I think if you've ever seen a pulley, you know that normally a pulley will have quite a bit of stuff around the outside edges of the pulley. Like there's a channel of some material where the string goes through. Then it's kind of thin, and there's like a flat piece of metal or plastic, and then it bulges back up around the pulley, around the hub of the pulley itself. So the mass is distributed a little bit weird. And anytime you have more mass out at a large radius, that's going to basically result in a bigger moment of inertia. So this seems fairly consistent with that. I would need a little bit more details about the actual shape, picture, and that sort of stuff. But in this case, it worked out just fine. And like I said, I think it's a fairly reasonable to be a little bit bigger than what a cylinder would be. So any questions on that? All right. So the next problem, I left a page there to do some work, but I'm going to let's see if I can do this. See if it'll let me remove the page. Nope. I will do that later. I'll do it before I post a note. So here's another problem. So now we're going to imagine the exact same pulley that we just worked on. Now, remember that pulley came not only with a mass and a radius, but it also came with a friction force. So we're going to assume the same sort of things happening here with that friction force. But it says a mass of 2.04 kilograms hangs from one side of the pulley detailed in the previous example. What angular acceleration will the pulley experience? What will be the linear acceleration of a point on the edge of the pulley? And C, what is the tension in the rope? So again, we're going to have the same sort of scenario as we did before. We're going to have a circular pulley. The radius of that pulley is R, and R is equal to 0.400 meters. We have a mass of the pulley M, and that is 4.25 kilograms. And this time we actually have a mass hanging from it. So what I'm going to draw here is a rope pointing straight down, and then on this is M, and I'm going to say little m is equal to 2.04 kilograms. Okay. We also have a friction force that causes a tension this way, and that's tau friction. The tau friction is going to be the same number we had before, which was 3.00 Newton meters. And I'm going to do the same thing I did before, which says this is going to be a positive torque and this is going to be a positive direction. So my free body diagrams, which I can start now, I'm going to do solution. Actually, I don't want to do red. I mean blue. That's the one thing I don't want to do. I'm going to do solution. I'm going to use the summation of the torques is equal to I times alpha, and I'm going to use the summation of the force is equal to M times A. So first off, my free body diagram is going to look like this. There's R. And what I'm going to have is a tension T pulling down this way and a torque tau friction pulling this way. So the summation torques is equal to I times alpha is going to give me R, which is 0.400 meters times, now in this case, actually it should just be T, that's our positive torque, minus 3.00 Newton meters is equal to I, which we found was 0.5 kilogram meters squared. And all of that is going to be multiplied by alpha. So that's equation 1. Now we're also going to have a free body diagram here for M equals 2.04 kilograms. And what we have acting on it is a tension T and a force mg, which equals 20.0 newtons. Because if you take the 2.04 and multiply that by 9.80, you will get 20.0 newtons. Again, we're using down as the positive direction, so the summation forces equals mass times acceleration gives us 20.0 newtons minus T is equal to 2.04 kilograms times A, and that'll be equation 2. Anybody have any questions on that so far? All right, I'm going to take equation 2 and solve for T. And what I get is T is equal to 20.0 newtons minus 2.04 kilograms times A. And I'm going to call this 2 prime. Now I'm going to plug 2 prime into 1. And what I'll get is 0.400 meters times, now I'm going to write 20.0 newtons minus 2.04 kilograms times A. Now that's all just a tension. That's equal to 2.04. Ooh, excuse me. I'm going back to number 1. Let's not forget. So I have written something wrong. That is 0. Excuse me. That is minus. So all that minus 3.00 Newton meters. I don't like how that turned out. It looks like I put the decimal a little too close. So let's say 3.00 Newton meters is equal to 0.500 kilograms meters squared times alpha. Okay, so that's kind of helpful, but there's another equation we can use. Since the rope's not becoming slack, it's not stretching, and it's not sliding on the surface, then we also have equation 3, which is A is equal to R times alpha. So I can divide both sides, for instance, by 0.4. So divide both sides by 0.400 meters implies A over 0.400 meters is actually equal to A from equation 3. So that's what I'm going to do. When I do that, I now get 20.0 newtons minus 2.04 kilograms times A minus, now here's the tricky part, because the 0.4 I just realized was only multiplied by this first term. So when I divided it through, that's going to cause this 3.00 Newton meters. That's going to have to be divided by it as well. So I'll just go with it. It's not the end of the world, but it definitely wasn't what I was trying to do. So that's divided by 0.400 meters. And then on the other side, we're just going to get 0.500 kilograms meters squared. Now alpha over R is just going to be A. So now I have exactly one unknown in this. So I can take 0.4 or 3 divided by 0.4. That's the same thing as 30 divided by 4, which is 7.5. So I'm going to say 20.0 newtons minus 7.50 newtons is equal to, now I pull this over to the other side, the 2.04 kilograms A, I pull that to the other side, and that's going to give me 2.50. Well, actually, I can't add that yet. Oh, yes, one of these disappeared. And what happened to the other one? Oh, this one was kilograms. When I divided it by 0.4, that gave me a newtons. But the 2.04 kilograms times A, that was right. I'm working out the units right now to make sure everything I did was correct. So the 2.0 or the 20.0 newtons minus the 3 over the 0.4 does give me the 7.5 subtracted from the 20. But when I add the 2.04 to the right-hand side, I get 2.04 kilograms times A, whereas I had 0.50 kilograms times A. So what I'm trying to make sense of is what happened when I divided through by the 0.4. So if I divided through by the 0.4, the alpha does become alpha over 0.400 meters, which is A, but I'm trying to make sense of what happens to the kilograms meter squared. Because obviously when I divided by the M, that could in principle take it away, but it only seems reasonable to me for me to take away one of them. This is a bit of a conundrum. I tell you what, I thought this was going to work the way I did it. It's making a mess. So what I'm going to do is, you see where it says T 2 prime T equals 20 newtons minus T.04. I'm going to stick with that, but I'm not going to divide both sides by the 0.4. So what I'm going to do is just erase that last step, because that's making something ugly that I haven't thought out ahead of time. And though I'm confident it'll work out right, I don't think it's fair of me to try to figure out how to make that work right in real time. So I'm not, and I don't know why I just stopped erasing that blue part, because that was the part I wanted to erase. Okay, so I'm not doing this part. Okay, so what I will do is I'm going to go ahead and distribute that 0.4 times 2 times 20. You all right, Shawnee? Shawnee? Okay. Sorry, I just heard something drop in the kitchen, just checking on everything. So if I multiply 4/10 times 20, that's the same thing as 2 times 4. That's going to become the 8. So I'll get 8. Whoa, no. So I'm going to get 8.00 Newton meters minus, now I've got to multiply the 0.4 times 2.04. So if I divided that by 10, that'd be 0.204. And then I multiplied it by 4, that'd be 0.816. So 0.816. And this is going to be basically kilogram meters, because I had a kilogram there already and I just multiplied it by a meter. But now that's times A. And then I'm going to say minus 3.00 Newton meters here as well. And then I am going to say that alpha is in fact A over R. That was a problem. So alpha is in fact A over R. I just figured out the conundrum. So 0.500 kilograms meters squared times A over 0.400 meters. That's really what's going on now. So basically A equals R times alpha says that alpha is equal to A over R. So I can just substitute A over 0.400 there. And that works out just fine. 0.5 divided by 0.4, by the way, is the same thing as 5 divided by 4. So it would be 0.8. So now I've got 8 minus 3 on the left-hand side here. Notice those are the only two without A's in it. So this is 5.00 Newton meters. If I pull the A term over to the other side, that's going to become 0.816 kilograms meters times A. And then that's plus, now 0.4, like a 0.5 divided by 0.4. Oh, I said that was 0.8. That's reading that upside down clearly. So 0.5 divided by 0.4 is the same thing as 5 divided by 4, which is the same thing as just basically 5/4, which I can say is 1.25. So this is going to be 1.25, and that's kilograms times meters, because it was meters squared, but I just divided by one of them. So 1.25 kilogram meters times A. And of course, you can combine those two and say 0.816. I'll double check that math, make sure I remembered it or I did it correctly. So 0.4 times 2.04, I said was 0.816. And I'm right about that. So I'm going to take that and add to it 1.25. And that gives me 2.06. And actually 2.066 kilograms meters times A. So I've got 5 Newton meters equals 2.066 A. So all I have to do is divide 5 by 2.066. and that gives me 2.42. So I get 2.42 meters per second every second is equal to A. So, and that's A being the very edge of it. So this is actually the answer to part B. And then to part A, alpha is equal to A over R. So it's going to be 2.42. Oops, I definitely didn't mean to write all that in blue. I really shouldn't waste my time doing this, but I am. Okay. So alpha is equal to A over R, which equals 2.42. The extra digit that I'm leaving off is 0 and then a 1. So it's really not much need to add them, but I will just for consistency, meters per second per second. And now I'm going to divide that by 0.400 meters. And that's going to give me 6.05. That's 6.05 radians per second per second. So that's the angular acceleration. Any questions on that? Okay, and you can also see from 2' how to get t. And t is just going to be 20 minus 2.04 times A, which we found was 2.42. So 20 minus, and here's where you use parentheses just to be careful. But your calculator knows that you're supposed to carry out multiplication before you do subtraction. But you might not, so you can sometimes accidentally do some crazy stuff. But what I'm doing right here is I did 2.04 times 2.42, and I'm subtracting that from 20, and that gives me 15.1. Newtons. So that's actually what the tension is. Any question on that? I don't like how I wrote that 15. I really don't like how I wrote it when I wrote it with the wrong color. So 15.1, and I'll just remind everybody that this was 20.0 newtons minus 2.04 kilograms times 2.42 meters per second every second. And that's how I got it. So anybody have any questions on that now? Nothing. All right, so that's another type of dynamics problem. Another one that's sort of instructive and also allows us to see something very specific that happens. One of the laws of physics that we sort of employ from time to time when we're solving these problems is if, for instance, you have a pole. Let's say you have a vertical pole sitting like this, or the Leaning Tower of Pisa or something like that. Okay, if you go to calculate what happens, like what kinds of acceleration this object gets if it started to fall over, you would ask yourself exactly where does the force of gravity act on this? And you can say, well, the gravity acts on the very top, it acts on the very middle, it acts on the very bottom, and it acts sort of equally strong and all those different things. But in fact, the way you do this is when you have an extended body like that, if you want to know translationally what's going to happen, and even rotationally what's going to happen, it's going to behave as if the force that's acting on it is acting on the center of mass of the object. So Your book actually gives you an example like this, but it explicitly tells you in the problem to do that. So I just want you to know that, for a uniform body, well, for uniform bodies, the center of mass is the geometric center. But for all bodies, basically the force of gravity, for instance, will act at the center of mass for that object, whether it's uniform or not. So sometimes you might actually have to go through and calculate the center of mass first. I mean, if you're actually doing a real problem, things aren't always having their geometric center as the center of mass. So sometimes you might actually have to calculate the center of mass. But in this case, again, I left an extra page, but here it is. So what we're imagining here is we have a length of rod whose length is L, and we're assuming we know that, and whose mass is capital M, and we're assuming we know that. And then we're saying that its center of mass is in fact the geometric center, which is a distance L/2 from the hinge, basically. So I'm sort of ignoring the small distance between the center of that little circular pin that looks like there's in the hinge out to whatever point on the rod. So that's just part of what I'm doing here. The main thing is it's going to rotate about that center of that little hinge, but I'm ignoring the small difference in the center of the hinge to where I drew the end of these arrows. It doesn't really matter too much. So what we're wanting to know here is what is the angular acceleration alpha and the linear acceleration of the right end the instant it is released. So what you can imagine is someone's just holding this rod up horizontally, and then all of a sudden someone's going to lift it, release it, and it's just going to fall because gravity is going to pull on it. So what we're wanting to know is what is the linear acceleration of that far right end and what is the angular acceleration. So that's what we're going to work out here. So solution. Again, we're going to use the summation of the torques is equal to I times alpha. In this case, I'm going to say something rotating this way is a positive torque. In other words, this time I'm saying clockwise rotation is a positive torque. And it turns out this one just has torques acting on it. So I don't have to worry much about what's going to happen to the left and to the right and all that stuff like I did with a pulley. So if I draw my free body diagram, what it's going to look like is basically, whoa, Nelly. What it's going to look like is basically this. So this length from here to here is L. Its mass is M. And then I'm also going to say there's a length from here to here, which is the center of mass. And at that point, we have a force acting that is mg and is perpendicular. Okay. So now I can say the summation of the torques is equal to I times alpha. I derived for you before the moment of inertia of a rod rotating about its end. That was 1/3 ml squared. Rotating about its center was 1/12 ml squared. In this case, we're doing the end. So what I'm going to say is there's a clockwise torque, and that clockwise torque is going to be L/2 times M times G. And since they're perpendicular, that means the sign doesn't need to be included because the sine of 90 is 1. Now it is equal to 1/3 ml squared. That's the I. And then times alpha. Okay. And you can see in this case that the 2's cancel out and the m's cancel out. The m's canceling out is sort of like Galileo's big conclusion that acceleration is independent of mass. And that is true. If you look at Newton's second law, for instance, you could say A is equal to the total force divided by the mass. Well, the gravitational force is directly proportional to the mass. So you see that the mass in the top cancels out with the mass in the bottom. That's why you always get the same acceleration, which goes to g. So that's really what's going on here. But in the end of all this, we can now say alpha is actually equal to, notice I didn't do this x out part, but you see there's an L squared on this side and there's only an L on this side. So we're left with an L on the right hand side, and we're going to see that alpha is in fact equal to, ooh, why did I write 1/2? That was stupid. I just finished telling you guys it was 1/3. I don't know why I wrote 1/2. Let's fix that real quick. And let's fix that. Okay. Sorry about that, everybody. Make sure you correct that in your notes. This side is L over 2. This side is 1/3 ml squared. So what we're going to do when we get alpha is we're going to divide both sides by 1/3, which is the same thing as multiplying by 3. So I'm going to get 3/2 on is what alpha is proportional to. The m's are gone, but we do have a g over an L, and that is the angular acceleration. Any question on that? Now the other part, A, we want the acceleration at the end. So A is equal to L times alpha, suggests that A is equal to L times 3/2 G over L. Ooh, I could have written that a little uglier. This is equal to 3/2 G over L, which equals just 3/2 G. And that's sort of the result that I wanted you to see. In this case, notice the end is going to act quite a bit differently than when you drop a ball in near the Earth's surface. When you drop a ball near the Earth's surface, if you can ignore air resistance, it's basically excuse me. It's basically going to fall at an acceleration of g equals 9.80 meters per second per second. But because the center of mass is where the gravity seems to act, then that particular part should ultimately accelerate at g. But since the end is twice as far from the axis as the center of mass, it's going to go in some sense like twice as fast. So that's ultimately what happens. And you see, maybe that's a little bit of an explanation why people get hit by trees when they come down and stuff like that, is not because they're just not paying attention or they lack experience, which obviously those things can be very important, but it could also be the fact that the things accelerate a lot quicker than they're used to. So the end would actually accelerate way faster than 9.8 meters per second per second. And if you've grown up running from things that are falling, knowing how fast they fall could actually be a hamperance or something that would hamper your success. So I don't know if hamperance is a word. I just made it up on the fly. So anybody have any questions on that? All right. So we've worked that problem, and that's really the 3 that I wrote up already. The other ones I wanted to cover was regarding conservation of energy, and then also a little bit about friction, so let me first do the conservation of energy one, and so you'll get an idea of how that works out, and then we'll go on. So does anybody have any questions about anything we've solved so far? Anybody need to see anything else? All right, so what I'm going to tell you here is it turns out that kinetic energy, which we knew as 1/2 mv squared, is going to become kinetic energy total, which equals 1/2 mv center of mass squared plus 1/2 I omega squared. In other words, when we're dealing with conservation of energy, if there's any friction forces that allow something, say, that would otherwise slide down an incline, now allows it to actually roll down an incline, then we're going to have both kinetic energy terms, because part of the energy is going to go to moving the center of mass, and the other part's going to go to rotating the rest of the mass around that center of mass. So let's see, let's calculate the velocity of a uniform sphere. Whoa. Of radius r and mass m when it rolls down an incline of height h, or no, assume it rolls without slipping. Okay. So I will draw a nice little incline. Let's say like this. Let's put a little mass up there. Let's say this height is y equal h. Okay. And then down here, I want to know v equals 0 up here, but v equals question mark down here. And after I'm done, I'm going to compare it to it sliding without friction. Okay. So let's work this out. What we have is solution. Now, what I've told you guys I like to use for conservation of energy is U initial plus kinetic energy initial, plus I added this other term. I'm going to say work put into it plus energy put into it is equal to U final plus kinetic energy final plus work out plus E loss. So that works as well. And using it this way, and we're assuming we're near the surface of the earth so that we're not, you know, a earth radii away from the surface of the earth. So the typical potential energy is just going to be m times g times h. It started at rest, so that term's 0. We're not putting any work in by someone pushing it or by spring loading a barrel and then shooting the ball out of it. And we're not putting any energy in, so we also have En equals 0. And then at the end, the potential energy is going to be 0. So I'll put a 0 there. But the kinetic energy is going to have to be 1/2 mv squared plus 1/2 I omega squared plus 0 plus 0. Now, we also have the added pleasure that it rolls without slipping. So rolls without slipping means V is equal to R omega. So this can be equation 1, this can be equation 2, and we can now apply them. And what we're going to have is mgh is equal to 1/2 mv squared plus 1/2. Now, here's the moment of inertia of a sphere rotated about its center of mass. That turns out to be 2/5 mr squared. And then times omega squared, but omega is v over r. So I'm going to say v over r quantity squared. So just for record, using equations 1 and 2, I got this result. Okay. So you can see what happens here when I square that v over r, the r squared is going to cancel out. and I will get mgh is equal to, oops, I should have also written this as the same m. I don't know why I wrote small there, but that's that. You can also see that the m's will cancel out. I'll show that in a second. But what we get here is 1/2 mv squared. And well, basically we get two terms with mv squared in it. So I'll put mv squared out in front. For the first term, I get a 1/2, but for the second term, I get a 2/5 times a 1/2. So that'd be a 1/5 like this. And of course, this is the same thing as 2/10 plus 5/10. So I get 7/10. Okay. You can now also see that the m's cancel out, which is nice. And now I have that g times h is equal to 7/10 v squared. So finally I can say v is equal to the square root of 10 over 7 times gh. You might recall from the chapters we did on kinematics, before we did conservation of energy, we found square root of 2gh when things started at rest. And you might even remember that from conservation of energy. Notice we got an entirely different quantity here for rolling without slipping. Anybody have any questions? Okay. So if we were to work the same thing with it sliding without friction, this is what would happen. So what about sliding without friction? Okay. Now you would probably think that sliding without friction is going to be slower than rolling without slipping. And you'd actually be wrong, and I'll explain to it why in a second, but explain it why that's the case in a second. But here we're going to start off with m times g times h, and all we have left is 1/2 mv squared. There is no rotational motion, so we don't have to include that. You can see already that the m's cancel out, and you get just plain v is equal to the square root of 2gh, as I advertised a second ago. Now, in order for that other answer to be 2gh, it would have needed to be a 14 up top. So we can tell v rolling, which I'll subscript over here, roll. So v roll is less than v slide. Now, what you got to think about this is, notice in the equation 1 that I wrote, some of the energy is going into 1/2 mv squared, whereas in this black equation I wrote down at the bottom, all of the mgh went into 1/2 mv squared. In this case, some of it goes into 1/2 mv squared, and because it's rolling without slipping, the two terms, the 1/2 I omega squared, are interconnected, so that you end up getting some fraction, and it's a very specific fraction because of this connection, has to go to the actual rotation as well. So yeah, you're losing some of that. And then also, if you think about it, well, of course, friction tends to slow things down. So why wouldn't you expect the rolling velocity, which required friction, to go slower than the sliding velocity, which had to happen with no friction? So any questions on that? All right, now the last problem I wanted to work, and we seem to have plenty of time, is I want to sort of work the same thing, but I'm going to work it with Newton's laws of motion. And I'm probably going to show you a couple of different ways to do it, because what I'm wanting to figure out is exactly how big does the friction force have to be to actually allow something to roll down an incline without slipping. So let's say if a uniformly spherical ball rolls down an incline without slipping what will be its acceleration and what friction force is required. Okay, so let's draw another inclined plane. I'm going to say there's our inclined plane. I'm not necessarily tied to that original example, but we're going to call this angle theta. That will be just fine. You could say that this is still going to be a height h, and that's fine as well. The main thing is I'm going to make use of the angle sine theta, or the angle theta. Okay. So here's our ball up here, and it'll have a mass m, and it will have a radius r, and we're assuming we know all this stuff, right? So now I'm going to draw a free body diagram. So what I'm going to do is put my y-axis and x-axis tilted like this. So this will be my y prime axis, say, and this will be my x prime axis. And from that, you can see that that angle is theta. And what I'm going to say right here is, let's do this. I'm going to say there is a normal force acting perpendicular to the surface. Oh, and I forgot to write a prime on that, so I'll put a prime right there. And then there's a a gravitational force acting straight downward, and that quantity is m times g. But that could actually be broken down into a vector that's this way. And notice if this angle that I have drawn is theta, then this angle is 90 minus theta, and this angle is theta again. So this one would be mg cosine theta. And then this guy, which points down the incline, would be mg sine theta. So from this, I'm going to say the summation of the forces in the y prime direction is equal to 0. And again, we're imagining the ball is just rolling down the incline. It's not bouncing up and down off the surface. So the acceleration in the y direction should be 0. And from this, I get Fn minus mg cosine theta is equal to 0, which gives us that the normal force is actually equal to mg cosine theta. And that's a creepy looking gravitational acceleration there. So leave it to my OCD to have to fix it. Okay, so that's going to be equation 1. We have that. Now I'm going to do the summation forces in the x prime direction is equal to mass times acceleration in the x prime direction. And in this case, I can see that my forces are, and I forgot friction. So let's go ahead and add that too. That's going to be in a negative direction. So I also have this force right here, which it's a static friction because we know that the bottom of the sphere doesn't move relative to the sphere, just like the bottom of a car tire doesn't move relative to the road when the car's going 60, unless it's skidding or spinning out. So it is a static friction, but we can't be sure that it's necessarily mu static times the normal force, because remember, static friction is less than or equal to mu static times the normal force. So I'm just going to call it plain F and leave it at that. And later we can compare it to mu s times the normal force if we want to, just to kind of get a coefficient of friction or something. So in this case, it looks like we have a mg sine theta minus F is equal to m times A. That's going to be equation 2. And I apologize for that G looking so bad. It looks quite bad off there, but that's a little better. So mg sine theta minus F is equal to ma. That's equation 2. Now I need to draw a free body diagram for the actual rotation of this body. So I can again tilt the axes like I had before, and that might help it a little bit. So what I'm going to do is draw like this. I'm going to draw my sphere right here. Okay. Now, we can look at this a couple different ways, but basically what I'm going to have here is there's going to be a force acting upward on it, and that's going to be the normal force. And that'll go right through the center of mass. There's going to be a friction force right here. There is also going to be a mg cosine theta that way. And there's also going to be a mg sine theta that way. And technically speaking, this mg sine theta should really act at the center of mass of this. So let me take that off and that off. So what I'm going to do is say this is my center of mass. I'm going to say I have this force. Oops. I have this force mg cosine theta acting there. I have this force mg sine theta acting there. And if I take the center as the center of rotation, or the pivot point as I call it, which is basically what you treat as the center of rotation of the system so that you can define your lever arm vector and stuff like that. With this one, now I can see the summation of the torques is equal to I times alpha. So if I actually choose that it's going to be that pivot point, you can see that the FG cosine theta, the FN, and the MG sine theta all go right through the center of mass, so they have no lever arm. So whoa, Nelly. So mg cosine theta and mg sine theta and Fn have lever arm equal to 0 implies torque is equal to 0. So really all we have is something that's tending to cause a rotation in the clockwise direction, which is consistent with the going down the incline in the positive x direction. So I'm going to call that a positive torque direction. So that's my sign convention. And in fact, what I'm going to say is R times F. Notice they are perpendicular to each other. R times F is equal to 2/5 mr squared, because that's the moment of inertia of the sphere, times alpha. Okay. And that's going to be equation 3. So I can, in principle, cancel out this r with that r. And ultimately, I get that F is going to be equal to 2/5 mr times alpha. But using equation, let's see, A is equal to r times alpha. That's equation 4. So if I use equation 4, I get F is equal to 2/5 m. Now, alpha is going to be a over r, so that's going to cancel out, and I just get 2/5 ma. So I have some formula for the friction right now, but that doesn't really do me any good until I solve for a. But now I can plug this into 2. I'm going to call this equation 5. So I'm going to plug 5 into equation 2. And from that, I'm going to get mg sine theta minus F, which we decided was, evidently I wrote it with a 2/2 here instead of a 2/5. So that's a 2/5, not a 2/2. So that's 2/5 ma is equal to ma. So I can pull the 2/5 over the other side. That's going to give me 2/5 plus 5/5 equals 7/5. So I get mg sine theta is equal to 7. Oops, no. Yeah, it does add. So it will be 7/5 m times a. So a is ultimately going to be equal to, notice the m's can cancel out now. So the a is going to be equal to 5/7 g sine theta. Now, if it slid down the incline, it would just be g sine theta. We've worked that problem out before. So now I have the acceleration is 5/7 g sine theta. So I have that. I could also say alpha is equal to a over r. So in this case, it's 5/7 g over r times the sine of theta. I've got that. But really what I want to know more than anything is really what is the friction force. So the friction force is going to be equal to, friction force we found was 2/5 m times a. So that's 2/5 m times 5/7 g sine theta. Notice I just used that right there. Okay. So now I can simplify a little bit. You see the 5s are going to cancel out. Oops. The 5s are going to cancel out, and that's going to give me 2/7 mg sine theta, and that's actually equal to the friction force. Actually, I don't want to do that. I'll do that there. Okay. Now, if you say F is equal to some constant times Fn, then you can see that that constant would be F divided by the normal force. And in this case, you'd get 2/7 mg sine theta over, remember our normal force was mg cosine theta. So you can actually say that it would actually equal 2/7 tangent theta. which relates again to something we found earlier about the minimum angle at which something must be inclined before it will overcome friction. Turns out to be the inverse tangent of the coefficient of static friction. So that's somewhat related. Now, the neat thing is you could actually have treated the bottom as the pivot point as well. And I did that earlier and got exactly the same answer. So that's kind of neat. But I will go ahead and call it a day. We've got about 4 minutes left. So you're welcome to stick around, ask me questions, and I'm not going to leave anyways until the last person leaves. So you're free to go, and let me know if I can do anything for you. John, I did set your test up, so make sure you can get that done. I set it for tomorrow, 11:59.
All right, thank you.
You're welcome.
Bye. Bye.
Bye-bye. Anybody have any questions? Alyssa, do you have any questions? Looks like she might be gone. All right.
No, I don't have any. Sorry. Thank you.
No problem. See you, Alyssa. Have a good one.
You too.
Bye-bye.